Good day to you. How are you doing? How's everything? I hope you enjoyed the last class. And the last class we talked about set theory. Then we talked about definition of sets, types of sets, we talked about Venn diagram, operation on sets, including intersection, union, and so on and so forth. We also talked about equivalent sets, the cardinality of the sets. So that the thing we discussed in the last class. Today, we are talking about lesson 2, which is the mapping function and relations. Mapping functions and relations. Before I go to that, I want to appreciate those of you that spend your time to listen to lesson 1 and see your requests for the access to the Adonai lecture with us to you. So I want to encourage you to continue. Today, as I said, we are looking at the lesson 2. Don't forget we have about 5 to 6 series or modules for this lecture. So lesson 2 is a understanding mapping function and relation. Mapping functions and relations. So without wasting our time, recall that a set is clearly defined as collection of well-defined objects. Collection of well-defined objects, and that is in our previous class. So things or number, and given two non-empty sets. Now set A and B. If there is a rule which assigns an element to a set A and a unique element to set B, then that is called mapping. So in a nutshell, today we are still talking about sets. So all the elements or what we're talking about, we're still talking about sets. So in mapping, we are still referring to sets in a way. Now let me take that again. So what do we call mapping? So if we have two non-empty sets, that is, that set must have at least an element. It must not be an empty set. A and B, two sets A and B, and there is a rule, there is a connection, there is a relationship that assign a value for x, then another value for y from x. That is the value in y. There's a connection, relationship between the value in y and x, and the such is called mapping. So the first set, which is set A, is called the domain, while the other one, the set B, is called the codomain of the mapping. So if the rule which associates each element, that is x, belong to A, you to recollect this sign in set, that is x is an element of A. A unique element y, which is an element of B, is denoted by f. So the function, so the mapping between the set A and B can be represented by any of the following diagrams. So which is called the arrow diagram. This is arrow diagram. So as you so read, so f is a function of A mapped to B. Function of A mapped to B. So which means f of x, and this f is x is a function of y is a function of x. So to see, so y is a function of x, which means that y depend on x. Y depend on x. So where y is the unique element in B, which corresponds to the element x in A. So the element y is called in B is called the image of x in A. So element y is the image of x in A. I know we are still going to give an example for us to understand it better. Or let me use it this way. As you are in class now, you are the image of your father or your mother. You represent your mother. There is a connection between you and your parents. So that is that. So if there's any element in B, so then there's a connection between that element in B and element in A. So that element in B is the image of the element in A. So the element, set A is the domain, while set B is the codomain. I don't want to take much of our time. So, and all the elements in B that represent or that serve as image of elements in A, they are called the range. They are called, so it's a subset. So the range is a subset of codomain. Not all elements in B in the codomain serve as image to elements in the domain, but all those elements that serve as an image to element in B in A, that is from the domain, they are called the range. So by the time we go into the example, the diagram, you understand it better. Now if f function of a map to b is a function set, is a mapping set a into the set b, then the range is usually denoted by what? F of a, yes, so f of a is the subset of the codomain. So hence f of a belong to what? To b. So the function of what? That f of the image of a, the image is a subset of the element in b in the codomain. Is a subset of the element in codomain. Now let's now go into the illustration so that you understand it better. Now look at the diagram below. Look at this example 1 and the diagram below here. Given that P is a set, don't forget, is contained in curly bracket as I've mentioned in the earlier class. Likewise Q. So the elements in P, they are W, X, Y, Z. Y elements in Q are A, B, F, E, G. So let the mapping be what? P map to Q be defined by the diagram below here. Now you can see this is the arrow diagram I've mentioned before. Now the image of W in P is H in Q. You can see the arrow run from W to what? To Q. So all the elements in P, that is W, X, Y, Z, they are the domain. While all the elements in Q, A, H, F, E, G, they are the codomain. Now look at the image of W in P is H in Q. The image of X in P is the E in Q. The image of Y in P is the A in what? In Q. While the image of Z in P is the H in Q. Now you see that there is, so W and Z, yes, they have the same image in Q. Yes, it happened that way. I will explain that later. So it happens that way. There are some functions that produce the same image, different elements, and produce image. Okay, let's say for instance, so let me go to the notepad. You can see the notepad now. So let's look at this function. Y is equal to x squared plus 1. Find y when x is equal to 1 and when x is equal to minus 1. So the solution, you could see that when x is equal to 1, then y is x squared plus 1. That is 1 squared is 1 plus 1 is 2. Likewise, when x is equal to minus 1, minus 1 squared plus 1 also is also what? 1 plus 1, which is 2. So don't forget minus 1 squared will give what? 1. So minus times minus give us 1. So you can see that the two elements, they are not the same. Minus 1 and plus 1, they are not the same, but they produce the same image as what? As 2. So similar thing happen here. So W is possible that what? W and Z, they can have the same image as H, just as minus 1 and plus 1 produce the same image in the function showed earlier. Now this is what they call the arrow diagram. You can see clearly now f of W is H, as I've said before. Yes, f of X is equal to E, f of Y is A, and f of Z is H as well. So A is the image of Y under the mapping F. So we observe that although every element of P has a unique image in Q, not all the elements of Q are images of elements in P. Yes, you could see that F and G stand alone. They does not represent any, they do not serve as image of any elements in P, so to say. So not all. So now the AHE, I've said earlier on, they are the range. Because and they are subset of Q. So because A, H, and E serve as image of elements from P, they are the representative of elements from P in Q. They represent W, Z, Y, and W, X, Y, and Z, so to say. So A, H, and E, they are the range. So they serve as image of elements from P. So they are the range, and they are the range. At the same time, they are the subset. They are subset of Q. So then P is this. It's called the domain, and the Q is A, B, F, E, G. They are the codomain I've mentioned earlier before. Why the set A, H, E is the range? Yes, I've said it. They are the range because so we denote it as what? As R. So they are the range R. So and they are subset of Q. Look at this this statement, this symbolic statement, that's a R is a subset of Q. R belongs to what? Q. R is extracted from Q. So that's that. Let's look at an example now. Look at this example of the real life example of mapping. Look at this X. Let X be what? Be this NCG, where NCG that represent countries like Nigeria, like Cameroon and Ghana. And let Y be their capital. That's ABYKN. So where ABYKN represent Accra for Ghana, Abuja for Nigeria, Yaoundé Cameroon, Kinshasa, that's the Congo DR, and Nairobi for Kenya. Now, and let the mapping of F from map F from X set X into the set Y be the capital city of the corresponding countries of the country. So, and look at it in the diagram. So N is Nigeria, C is Cameroon, and G is Ghana. Now you can see the image of N in X is B, which is Abuja, according to the example, the instruction given. Then that of C is Yaoundé, which is Y, and that of G is A, is Accra. You could see that K and N, which is Kinshasa and Nairobi, it does not have what? It does not serve as image because their country was not mentioned in element X. It was not mentioned in element X. Only 3 countries was mentioned in X. So that's NCG. Why they are what? So they map to their image, their capital, YAB. Now, once again, so we observe that X is the domain, yes. Y is the codomain. So the set Y, the set YAB is the range. So that is F of N is B. That is the capital of Nigeria is Abuja, which is B. Capital of Cameroon is Y, which is Yaoundé, and capital of Ghana is Accra. So that is F of N is equal to B, F of C is equal to Y, and F of T is equal to A. So our YAB is what we call the range, and you see that range is part of the element of Y. So it's part of the element of Y. So YAB is the range. So a function is mapping. Host codomain is set of what number? Let's go to function now. The function is a mapping. Host codomain is a set of numbers. Host codomain is a set of numbers. Now let's look at this diagram now. So X is a set, Y is another set, so non-empty set, so to say. So the elements in X are 2, 3, 4, 6, and in Y is a 5, 7, 9, 13. So we can see that the image of 2 is 5, the image of 3 is 7, and the image of 4 is 9, and the image of 6 is 13. So both domain and codomain, they are set of numbers. So then the set is what is that's the what the mapping is a function. So we observe that 5 is the F, that's the image of 2, and I've mentioned that earlier. So look at it. Then the image of 3 is 7, the image of 4 is 9, and the image of 6 is 13. So we can discover that the rule which can associate an element from X to an element in Y, it appears that when 1 is added to this twice an element in X, it produces the corresponding image. So which means the function is a 2x plus 1. This function is 2x plus 1. The function, so f of x is this, so or y is equal to this, so it's 2x plus 1. Let me take it to this side. Function is 2x plus 1. So f of x now is equal to 2x plus 1, or y is equal to 2x plus 1, which when x is what is 2, that is 2 times 2 plus 1, that's a 5. So we can see that the image of 2 is 5. The image of 2 is 5. So let's look at the relationship that show. Yes, the relationship of f is not a what. Now look at this. Now look at this. Look at this. Consider the relationship shown in the arrow diagram below. So p to this one and this to this. So the relationship f is not a mapping, not because g is not an f image of any element, but because q, which is in x, has no image in what? In y. Yes, this one, there is a particular element in x that has no image in y. So this is not a mapping. It is not. So all the elements, look at the example given before, all the elements in x in the domain, they must have at least an image in what? In in the codomain, which is Y. But this one is not a mapping because P has an image E, Q has no image, R has an image what? Image F. So this is not a mapping. Look at this one too. Look at this one too. This is not a mapping as well. This is not a mapping as well. You know why? Because I've told, okay, let's U as image this Y, W also has image Y, which I've explained earlier. I've explained it earlier. Look at this. Look at this. I've explained this earlier that it is possible. Look at this. When x is 1 on 1 and when x is minus 1, it is possible they have the same image. But here you could see that V claim to have two images. It is not possible. V cannot have what? Two images. As you are, you can't. So yes, you. Okay, let me go to that. V cannot have what? Have two images. It's not possible. It's only what? Only one what? Image. Or let me put it this way. It is wrong for two parents to claim one child. No, two different fathers to one child. It is not possible. It's not possible. So a father can claim many children, but it is not possible that what two parents claim what? Claim one child. So this is what the case that happened here. So this one has to what? Two images here. It is not what? It's not possible. So now it's not a map because P has two images in the codomain and X and Y are what? Are the image of B. No. So this does not satisfy the uniqueness property of image of elements in the domain. It doesn't satisfy the property at all. So it's not possible that for B to have two images. Don't forget, a two elements can have one image in the codomain. Two elements can have one image in the codomain, but one element cannot have two images in the codomain. Two elements from the domain cannot have two. One element from the domain cannot have two images in the codomain. Yes. So therefore, the value of x is equal to 1. This is equal to the value of y when x is equal to minus 1, which is equal to 2. So both elements 1 and minus 1 is in the domain has the same image of 2 in the codomain. So two elements from domain can have the same image in the codomain, but two elements in the codomain cannot serve as image of an element in the domain. So that is it. So two elements in the codomain cannot serve as image of an element in the domain. So I hope you get that clear. Now let's look at the example again. Consider the relationship or the relation. This now. Look at this. The image of A is what? Is a S. The image of B is a B. The image of D is also P, and the image of this is what it is. So this is a mapping because every element of the domain has image in the codomain, and the image is unique for every element of the domain. The image is quite unique for element. So the domain X A B C D. The domain is a PQRS T. PQRST, yes. So the range, now don't forget the range, they are the elements in the codomain that serve as image or images to elements in the images in the elements in the domain. So PQS, they are the range. So two important properties need to be emphasized here if a relation is to be mapping or a function. There are now every element of the domain must have as an image in the codomain, and the image of every element of its domain is unique. Of its domain is unique. Yes, it must be what? It must be unique. So that is what you have here. So for us to have a mapping or a function, these two statements must be satisfied. That is, every element of the domain must have an image in the codomain, and the image of every element of its domain is what? Is unique. Must be unique. Yes. So unlike this one, this is not a mapping. This is not a mapping. Likewise, this is not a mapping as well because V has two images. It is not possible. Like I said earlier on, two parents cannot claim one child. And these two different fathers, even or two different mothers cannot claim one child. So now, a mapping may sometimes be regarded as a set of ordered pairs. Yes, you can see that's a x, y. That's x and f of x, x and function. Don't forget y is a function of what? Of x. Y is equal to f of x. So it's ordered pair, like as we have it in coordinate. And don't forget, it must be contained in what? In curly bracket, because it's a set. It's a set. So the x set must be contained in curly bracket. Though it's ordered pair, but must be contained in curly bracket. So sorry. Yes. Yes. So now look at this now. Is there a set of set notation from mapping f? Diagram can be defined as a f is equal to f. Now f is equal to what? A comma y. That a to y, yes. The image of a is y, and the image of c is a x, and the image of b is a z. So let's talk about types of mapping now. Types of mapping. We have one-to-one mapping. One-to-one mapping. We have onto mapping. We have composite. So let's start with one-to-one. Now let x be a map to y. Let f be a function of x to y. Be the mapping that has established corresponding between x and y. So the mapping f is called one-to-one if different elements in domain x has different image in a codomain y. So different elements have different what images. So different, just like it's like a governor to a state. Yes, a governor to a state. Let me put that, use that example here. Okay, it's even the mapping which associates each state in Nigeria with governor is a one-to-one. Yes. At no time should we have two governors in a state. That's a constitutional crisis. It cannot happen. So only one governor at a time. We can have one governor, but one governor at a time. So as we are talking now, only one governor govern a state now. So that example of a one-to-one. Likewise, in a country, one president to a country, one president to a country. So the mapping which are assigned each university in West, okay, we have to vice chancellor. Yes, one-to-one as well. We can't have two vice chancellors in a university at the time. No, it's not possible. We can't have two rectors at the time. Only one. So that's an example, perfect example of one-to-one mapping. It's an example of one-to-one mapping. So let's look at this now. So this is a perfect example of what I gave you the other time. Look at this. So be a set of real numbers to mapping such this. So the function is a y is equal to x squared plus 1. Y is equal to x squared plus 1. Let me see if I have a similar here. Yes, okay, y is equal to x squared plus 1. Yes, it's here. So this is a perfect example. Now look at it now. Two elements from the codomain has one image from the domain because of the function, because x squared will give us minus 1 squared will give us 1, minus 2 squared will give us what? 4. So that is that. So the range here is 2 and 5. The range here is 2 and 5. You could see that the arrow diagram. So f of minus 1 is equal to f of 1, and f of minus 2 is equal to f of 2. Whereas minus 1 is not equal to minus 2. So the elements, they are unique and they have the same image. Hence the mapping is not what? This is not one-to-one. This is not one-to-one mapping. This is not one-to-one mapping. So now let's look at what this mapping now. This is an example of one-to-one. You can see minus 2 to minus 1, 1 to 5, and so this is an example of a one-to-one mapping. So the mapping, for example, 9 here is one-to-one. Now let's look at onto now. Onto mapping now. For onto mapping, okay, look at the example. If every element of the codomain is an image of at least one element in the domain, every element in the codomain is an image of at least one element in domain. So let's look at this. Let's look at this. Let's look at example 12. Oh, look at this example now. That's a is a set of numbers z minus 1, 0, and 1, and we have the function y is what? X raised to the power 3. So then the mapping is not only an onto mapping, but it's also a one-to-one mapping. Now let me go to the notepad now. I have this example here. Yes, this is the example. So we have the domain, the element in domain that is minus 1, 0, and 1, and the function is y is equal to x raised to the power 3, which is f of x. So when x is minus 1, y is also minus 1, because minus 1 raised to the power 3 gives us minus 1. When x is 0, it is what? It's also 0, and when x is 1, it's also 1. So the other pair is what? Minus 1, minus 1, 0, 0, 1, so the image of -1 is -1, the image of 0 is 0, and the image of 1 is also 1 as well. So that kind of one is what is onto, and it's also one-to-one. It's onto and is a one-to-one mapping. It's also, and it's one-to-one. Look at this one. Look at this. So the mapping is not onto, because Z is an element in key, and it's not an image of any element in the domain P. So hence the range is not equal to the codomain. The range is not equal to the codomain. So it's not an onto mapping. So wait, okay. For the onto mapping, every element of the codomain is an image of the at least one, and every member of the codomain is an image of at least one element, one member of the codomain. So the range of an onto mapping is equal to the codomain, yes. Which means in the onto mapping, every element in codomain must serve as an image of an element in the domain. So in such a case, so all the elements in the codomain, they serve as range. So the codomain says is equal to as range. But for this one, no. So the codomain is not the same thing as range, because there's an element Z, which has no, it does not serve as an image of any elements. So look at this now. Look at this. The range of the mapping is equal to the codomain, hence it is onto mapping. So it is not, however, it's not one-to-one. It's not one-to-one because Y and W, they share the same image. Y and W share the same image. So it is a onto mapping, because every element in the codomain serve as image, and all the elements in the codomain, they are the range. So the codomain is equal to the range. So this is a onto mapping, but this is not one-to-one. Look at, this is an example of one-to-one. This is an example of one-to-one. So one element marry another element in the codomain. One element in the domain pick an image in the codomain. So identity mapping now. So the identity mapping is the mapping which takes an element onto itself. An element onto itself. This is X to X, Y to Y, Z to Z. So a perfect example of identity mapping is this. This this -1, 0, and 1. If you look at it, the image -1 take -1 to itself, 0 take 0 to itself, 1 take 1 to itself. So this is a perfect example of an identity mapping. So let me put it here. Identity mapping. So these are types of mapping, identity mapping. Now let's move on. Let's move on to constant mapping. So for constant mapping now, so which assign every element in X the same image K. So then f of c is what is called the constant mapping. Fc is called the constant mapping if every element in X is equal to K, where K is the constant. So this is a graphical representation of a constant mapping. Okay, yes. Look at it. K is equal to what? F of X is equal to what? The constant. That is all the elements in the domain, they have just one image, and the image is what? It's just one. That's what? Constant. So that is a constant. Look at it. So okay. An essential feature of the constant mapping is illustrated above. The range consists of only one element. Another feature is illustrated above, and that the graph is a straight line parallel to the earth, horizontal. So it's a straight line parallel to the horizontal. So let me give you an example of this constant mapping. In quadratic equation, if you recollect, at the point, the constant is that the value will remain the same. When we are doing the table, the value remain the same. So that is when x is equal to 0, then y is what? Is constant. When x is equal to 0, let's say we have the function y is equal to 2x squared plus 2x plus 2 now plus minus 2. So when x is equal to 0, so the constant is what? Is minus 2. The constant is minus 2, and at every point of the value of what? X. So once it is 0, it is what? So that is an example of a constant mapping. That's an example of constant mapping. So all of them, they have. So perfect example is what is a straight line and parallel to the horizontal, to the x axis. So let's look at the composite mapping. Now that's the last part for this lecture. Composite mapping. Look at this. The f of what? Seg x to what? Z, and z to what? Y. And look at the diagram. So now the image of x is what? Is in z, and z itself serve as what? As domain to what? To z, to y. Let me take that again. The element, so this is set x, y, z. So set x is the what? Is the domain, and the codomain to set x is what? Is z, and z itself is also a what? Domain to a codomain, that is set what? Set y. Now the mapping the element in x and produce an image in z. So that's the mapping G takes an element in z and produce an image in y. The mapping G of f takes an element in x and produce an image in y via z. Look at what? Look at p. P, yes, look at G of p now is equal to what? G of a is equal to x. So the image of p in, okay, the image of p in z is a, and the image of p in y is x through a, So that is what the mapping. Look at what can this. Look at the p now for q now, c and that, and x as well, and for r now is d in y and z in z. Okay, so sorry, d in z and z in y. That of s is a p in z and z in y. So the mapping is called a composite mapping. It's sometimes written as what? GF. So the composite mapping can also represent, that's a vertically vectorial, as illustrated below. That is what okay, I wanted to remember that resultant, yet resultant, just like in vector, the resultant. So resultant of a g and f is what? G of f. So is this the resultant force. You recollect that in your physics or in further math. So now let's look at the example. Consider two examples here. Let f be a function of x to y and g be a function of y to y, y to z. The mapping on the set of real numbers defined by, now the function of x is a x plus 1, and that of g of what? Function of y. G is a function of y. That's a y plus 1 all squared. So we have to find what? G of f. That g is a function of f, which is what? This. I'm still going to what? I'll take you to the notepad where it is well explained. We are going to consider these two examples. Then likewise, let the mapping f and g be on the set of real numbers. Be defined as f of x equal to 2x squared plus minus 3, and g of x is equal to x squared, x plus 1. Now find gf and fg. Let's look at it if it is a commutative. So let's look at it commutative. So this is the example, this is its solution, but let me take you to notepad where it is well explained. Now this is the notepad where it is what? Well explained. Yes. Now, so now the first one now. So f of x is what? The x plus 1, and g of x is y plus 1 all square. Sorry, y plus 1 all square. Y plus 1 all square. Yeah. Now we have to find g of f now. So g of f now is what? G f of x. You keep g, you what? Right now, what is f of x? That's x plus 1. That's x plus 1 here. That's x plus 1. X plus 1 here. That's, and you keep what? G now. Don't forget g is a function of y, which is y plus 1 all square. Now, second one now. So this is what? Now what? Substitute g now. The function of what? Of y now. That is, whenever you see x, you write the whole of this y. The whole of y is a y plus what? That's y plus 1 all square. Yes, that's okay, x plus 1, then plus the 1 all what? All square. Now x plus 1, this is which is a y plus 1. Whenever you see this y now, whenever you see y, you put x plus 1 there. You can see. So put x plus 1 there, then this plus 1 here, then square. That is what? G, or that's that of g now. So we now simplify it now. which is x plus what? Plus 2. Yes, you open the bracket now, this x plus 2 all square, and that gives us this one, x plus 2 square. So then it's simplified now, that gives us x square plus 4x plus 4. Then the second one now, also on composite. So we have f of x is 2x squared minus 3, and g of x is x plus 1. Find gf and fg. Now let's find g of now. So you keep your g and write out the function of what? F of x now, which is 2x squared minus 3. Look at it. G now, 2x squared minus 3. Now to now put in g now, whatever you see x now, you put what? This yes, put this x minus what? X minus 1. Okay, sorry, okay, sorry. This is g of x. Before you keep g and write out what the this one, that's the f of x. This is x squared, 2x squared minus what? Minus 3 is here now, and the other one is what? X squared plus 1. So whatever you see x now, you put this 2x squared minus 3. That is for what? For that of g. Then this minus 1 that is here, this minus 1. So this minus 1. Then you simplify now. So this is 2x squared minus 2, because minus 3 plus 1 give us minus 2. And you simplify now, so it give us 2x squared minus 2. You can factorize to be 2 into x squared minus 1. Then likewise, the other one, fg now. You keep f and write out what? G. Your g is what? X squared plus 1. So g of x is x squared plus 1. Then the other one is 2x squared, yes, minus 3. So write your 2. Whenever you see x now, you put what? X plus 1. Then square it. You're substituting for what? For f of x now. Then minus 3. This minus 3. So begin to simplify now. That's 2 into x squared. Yes. No, sorry. 2 into what? X squared plus what? 2x plus what? Plus 1 minus minus 3. And that gives us what? 2x squared plus 4x plus 2 minus 3. So sorry, I opened what? The brackets here. Yes, open the brackets here, and that's what we get here. So yes, 2x squared plus what? Plus 2x plus 1, then minus what? Minus 3. You for this one, you expand this one first. Expand this, yes, expand the x squared plus 1, and that gives us what? This one, that's x squared plus 2x and plus 1. Then multiply it by 2. Don't forget this 3 stand alone minus 3 stand alone. Then after that, simplify everything and give us this. So we observe that g of x, gf is not equal to what? Fg. So it's not commutative. It is not commutative, but it's associative. So 2x, g of x, f of x now is what it is, and y. Okay, we observe that. So this is not part of it. It's not part of it. So let's go back to the main material. So that is the example we want to give there. Then you can lay your hand on some of these exercises here. So some of these exercises you can lay your hand on it. So next class now we talk about the concept of permutation and combination. So thank you for listening.